To this stage in the course, NMR spectroscopy has focused on proton and carbon-13 nuclei. We previously discussed how carbon-13 NMR is complicated by the low natural abundance of the carbon-13 isotope, along with its weak receptivity. And one of the tricks that allows us to effectively collect carbon-13 NMR spectroscopy has been inverse detection of carbon-13 from attached or nearby proton nuclei. For organic compounds, the most common elements are carbon, hydrogen, nitrogen, and oxygen. The most common isotope of nitrogen is nitrogen-14, but that has nuclear spin of 1 and has not been widely used. However, N15 NMR spectroscopy has been developed. Nitrogen-15 has spin 1/2. Unfortunately, it has a low natural abundance and very low relative receptivity. But once again, inverse detection of nitrogen-15 by attached or nearby proton nuclei has allowed for nitrogen-15 NMR spectroscopy to be developed to some extent. Oxygen-17 has some potential. Craig Hill's laboratory at Emory has in the past done some work with oxygen-17 NMR, but I will not discuss that any further in this course. The other nuclei that I will mention will be fluorine-19, spin 1/2, 100% natural abundance, and a receptivity that is similar to that of the proton. So this is very effective and practical spectroscopy if fluorine atoms are present in the substance. And then the last nucleus that we will cover in this course will be phosphorus-31, also spin 1/2, 100% natural abundance. It does have a low relative receptivity. However, phosphorus is very important in biomolecules, linking the nucleosides of DNA and RNA, also phosphorylation of proteins, and there are a number of small molecule drugs and chemical reagents that have phosphorus in those structures. The textbook has a section on silicon-29 NMR spectroscopy, but I will skip that section in favor of the other nuclei that I've just mentioned. This slide shows nitrogen-15 NMR spectra for a few representative compounds. Alkyl substituted amines are more shielded than sp2 hybridized amides or heterocycles, such as formamide and pyridine, respectively. These spectra are proton decoupled. Note that in the proton-coupled spectrum that there is an apparent pentet, and that is consistent with 2 hydrogens attached to the nitrogen and 2 hydrogens on the adjacent carbon atom, all of which happen to have a similar nitrogen-hydrogen coupling constant. This textbook uses what is commonly preferred, which is using N15 as the standard for 0 parts per million. IUPAC recommends N15 nitromethane as a standard, but that has yet to be widely adopted. But those can be interconverted by using the difference in chemical shift from nitromethane to ammonia. N15 NMR spectroscopy is most useful in a correlation with proton spectroscopy due to the opportunity for inverse detection to increase the sensitivity of the nitrogen 15 signal. This is used quite a bit in characterizing amides, particularly those of peptides, as shown in figure 6.6. In the textbook, they did not describe the solvent, but it is likely in a small amount of D2O to provide a deuterium lock for the instrument, but the majority solvent is 90% H2O because we don't want the protium atoms on the amides to completely exchange with deuterons. In this two-dimensional NMR spectrum, we have proton on one axis and N15 on the other axis. Notice that we have three distinct nitrogen chemical shifts in the range between 120 and 140 parts per million. For the corresponding proton signals, we see some difference in the chemical shifts between 8 and 9 parts per million, consistent with the ability of the amide NH to hydrogen bond, as well as the electron withdrawing effect from diamagnetic anisotropy of the attached carbonyl. The triplet at 8.7 parts per million probably corresponds with the NH of glycine, and so we can assign the nitrogen 15 signal at 125 parts per million to be the nitrogen that is attached to the glycine residue. The other two proton resonances that are both doublets correspond to either serine or glutamic acid, or glutamate, although those cannot really be discerned. This one-dimensional nitrogen 15 spectrum exemplifies what can be done with nitrogen 15 NMR spectroscopy, but also its limitations. At natural abundance, note that 500 milligrams of the sample are required. That's 1.4 millimoles. This also requires fairly high concentration in CDCl3 and a wider diameter NMR tube. And the probe of the NMR instrument also needs to be able to accommodate these wider diameter tubes. The acquisition time of 1 second with a relaxation delay of 7 seconds, 4,600 scans, adds up to more than 10 hours of instrument time. Note that only one of these nitrogen signals is particularly strong. That is for the nitro group with ortho protons, increasing the rate of nitrogen nuclear relaxation due to the nuclear Overhauser effect from the nearby protons. In contrast, N3 has a very weak signal. Notice that N3 is quite distant from any protons. In contrast, The proton nitrogen 15 heteronuclear multiple bond correlation experiment on the same compound can help us to assign all of the nitrogen atoms based on correlations with protons. Labeling along the N15 axis and the proton axis, it's worth noting that we only know about the nitrogen with this tiny little hump at C because of the 1D spectrum on the previous page. However, we can make correlations of nitrogen with protons. For nitrogen A, there's a correlation with protons F2. For nitrogen B, there's correlation with protons A, B, and C. There are no correlations with nitrogen C. Nitrogen D shows a correlation only with proton C. Nitrogen E shows correlations with protons D4, F2, and G2. The protons E, H2, and I3 have no correlations with nitrogens, indicating that there are too many bonds between protons and a nitrogen to show up in the multiple bond correlation experiment. Looking at the correlation of nitrogen A to F2, from the chemical shift of F2, that is consistent with a methylene group attached to a moderately electronegative nitrogen. For nitrogen B, correlating with protons A, B, and C, A, B, and C are in the aromatic region. I know it's difficult to see here, but A is an apparent singlet. B and C look like doublets. And so that's consistent with protons attached to the nitro-substituted benzene ring. So now we've assigned the nitro group as nitrogen B. For nitrogen D, we see only one correlation with an aromatic proton C. That makes sense with nitrogen D being the nitrogen number 1 on the isothiazole ring. And then nitrogen E, which correlates with aromatic D4, as well as with F2 and G2 of the alkyl region, is consistent with nitrogen 5. Nitrogen 3 is then too far away from any protons for correlation, and we can assign the remaining protons E, aromatic at the para position, and then H2 and I3 for the ethyl terminus.